Hey physics, welcome to another flipped lecture. We're going to be talking about hydrodynamics today, so we're continuing the study of fluids. Today we're going to let the fluids move, and we're going to talk about what happens when fluids move. This is admittedly a very complicated area. Your textbook gives you a lot of detail, but certainly not all of it. If you are intrigued by the study of physics, this is an area where there is a lot of work still being done to discover how fluids move in truth, and this applies to aerodynamic engineering, hydrodynamic engineering. You could study this and get a job working for an airplane company, a space agency, a race car, submarines, all kinds of things. You could even become a plumber with this kind of knowledge. So all kinds of things apply to hydrodynamics, and so let's get into it. So as we said, this is a very complicated area, and the true ways that fluids behave are very, very convoluted, complicated things. So for the sake of the introductory principles, we assume that a fluid is ideal. It's similar to an ideal string or an ideal pulley or an ideal, inclined plane. An ideal thing, we take away all the things that make it hard to work with, and we say we're going to pretend for a minute that this fluid flows smoothly, that it's all nicely moving around objects. We're going to ignore any kind of turbulence or things like that. That the fluid does not change its velocity with time at a given point. So if a fluid is moving through a pipe and I were to stick a little device in there that measured the velocity of the fluid, we're going to assume that the velocity doesn't change, that it's always going to be the same velocity. We're going to assume that the density of the fluid is uniform and constant throughout the fluid. Again, not always true. Some fluids are completely incompressible. Some fluids you actually can squeeze a little bit. And some fluids, like air, you can squeeze quite a bit. But for the sake of this introductory, a little jaunt through hydrodynamics, we're assuming that fluids are uniformly dense and that they are frictionless, that they actually move past things with no friction. We know that that's not true, but it makes the math a lot easier. So those are our fundamental assumptions here. We need to talk about types of flow. A streamline is a fictitious way of thinking, a model of how fluids flow, where we're going to draw some lines and say particles of the fluid move along these lines. Well, in truth, the particles of the fluid may be going all kinds of different directions, but we're going to draw lines for where the fluid particles flow, and we're going to call those streamlines. They don't exist, but they help make hydrodynamics easier to study. We're going to talk about two kinds of streamlines: laminar flow, where everything is parallel and moves nice and even along the pipe or the object that it's flowing past, and then turbulent flow, where there are bumps and twists in the flow. So let me show you some pictures here. Laminar flow would be like this, where the lines of water here, we're going to pretend are streamlines. They're actually not, but we're going to pretend that they are. And see how nice and smooth it is up here? Laminar flow. Everything is straight and smooth. Versus turbulent flow. Turbulent flow, where the water is rushing back on top of itself, and it's got bubbles and bumps, okay? That's turbulent flow. This is laminar flow. Here's another example. Up here we have laminar flow, and these are lines of smoke that we are using to represent streamlines, okay? But then when some object is placed in the air goes behind it and around it and swirls and gets not straight. And so that's turbulent flow. Two kinds of flow, laminar and turbulent. When we talk about flow continuity, this is an important concept. Because an ideal fluid is uniformly dense and it doesn't have any gaps in it, it completely fills its container, right? If something is moving with a certain volume per minute past a point in a pipe, we're going to assume that everywhere in that pipe it's moving at the same volume per minute, because otherwise you would have water compacting at some point where it slows down, or water thinning out at some point as it speeds up. And it doesn't happen that way. when a fluid moves uniformly. And so we have this principle of a continuous flow. Now there are some fluids like air where air can pile up or thin out, but liquids can't do that. So we talked about flow continuity. The volume flowing through a tube is going to be constant. The speed of any one particle may change, but the volume of the fluid as a whole is going to be constant. So we have a formula here to talk about that, where the volume of the flow is equal to the cross-sectional area of the tube. How big is the pipe or the container that it's flowing through? Okay, times the velocity of the individual particles, and this would of course be an average velocity. We understand that in truth some particles may be moving faster than others, but this is an average velocity of the particles moving past a certain point, times the time. And so this is very much like the volume of a cylinder or the volume of a prism. If you have the area of the base of the cylinder and its height, you know its volume. Similarly, the area of the pipe and then the time and the speed represent kind of the height concept. If you have the area of the tube, cross-sectional area of the tube, and how fast things are moving through it, you can get the volume of water or the volume of air or the volume of something that has flown through the tube in that amount of time. Okay? Take a moment and look at that again if you need to understand it a little bit deeper. The shape of the tube does not control the velocity. So again, think about the fact that it's the same volume of water moving through the tube. If the tube is bigger, then the same volume can move slower. Think about that for a moment. You have a little pipe and a big pipe. Same volume of water moving through. The volume of water is going to move slower through a big pipe. It's going to move faster through a little pipe because the same volume has to get through a smaller space, but the same volume through in the unit of time. So it's going to go faster. So the shape of the tube does not control the volume. The volume still moves. It controls the velocity, how fast it moves. The velocity will change to keep the same volume of water flowing. Consequently, fluids speed up when the cross-sectional area of the tube shrinks. So, got a formula for you. The area on one part of the pipe times the velocity of the particles, the average velocity of particles at that point in the pipe, is equal to the area of a pipe in another place. Maybe the pipe has changed size, times the velocity, the average velocity of the particles at that point in the pipe. So if I have a big pipe, I can have a small velocity. If I have a little pipe, I need to have a bigger velocity in order for them to still equal the same thing. Okay? All right. So here we have just a picture of that. If you have a large pipe, a large container through which a fluid is flowing, the cross-sectional area of that is very large. And in a certain unit of time, you might have this chunk of water flow through that pipe. In the same unit of time, if this water has been forced into a smaller opening, a smaller tube, you would have this body of water, which is the same volume as this body of water, flow through the pipe. But notice that the water here is moving faster. It's covered greater distance in that same unit of time. So here, this volume is equal to this volume. It only moved this far in a big pipe. It moved this far in a little pipe. So volume stays the same. Velocity does not. All right, let's apply this to a sample problem. I love potato cannons. I wish I could shoot a potato cannon with you. I was told by a police officer that I would go to jail if I did that, so I haven't done it here. But back in Arizona, where nobody cares if you fire potato cannons, I did it all the time. It's an awesome thing to do. You should go to Arizona and shoot a potato cannon too. But in a basic potato cannon, there's a firing chamber of a larger dimension than the barrel. to maximize the acceleration of the flow of gases against the potato. So the goal is to get this potato out the barrel of the gun really fast. I'm going to accelerate some gases in here by having an explosion, and then I'm going to make the gases go even faster by having the barrel be smaller than where the explosion was. Okay? So if a cannon's firing chamber has a radius of 10 centimeters, and the barrel's radius is 3.5 centimeters, and if the particles in the chamber are accelerated to move at 10 meters per second, how fast do particles in the barrel move? Should be do, not to, sorry. So here I have A1V1, A2V2, right? Area of the firing chamber, velocity of the particles in the firing chamber. Area of the barrel, velocity of the particles in the barrel. The area I need to remind myself of a circle is pi r squared. So pi times the radius squared is 314 square centimeters. Okay? Area of the barrel, 3.5 centimeters, is the radius squared times pi, 38.465 centimeters squared. So area 1, velocity 1, area 1, velocity 1 equals area 2 times an unknown velocity. So I need to just solve for the second velocity. So I'm going to multiply these together and I get this number. I'm going to divide now by this number and I get here. And I need to correct for significant digits. And my answer is 82. So 82 meters per second is the velocity of particles in that barrel, which will turn into the velocity of my potato. 82 meters per second. It's a pretty awesome potato cannon, and that's typically the kind of stuff you get. Okay? Here we go. Moving on to Bernoulli's Principle. Bernoulli's Principle talks about the relationship between height of a fluid and its velocity and its pressure. It is a very long equation, but you don't need to be afraid of it. Let's take it apart for a moment here. I'm going to say that the pressure at one point in a pipe is equal to half of that fluid's density. This is rho. Looks like a P, but it's actually the lowercase r in Greek, right? It's rho. 1/2 times the density of the fluid times the square of its velocity at that point. So here this is a speed term, a velocity term, and density plays a role. Okay? Plus, again, the density of the fluid times the gravitational constant, 9.81 meters per second squared, times the height above your point of reference at that point in the pipe. So this is a positional term. Pressure term, speed term, positional term for one part of the pipe is equal to all of those same things for the second part of the pipe. So what this is relating is, again, fluid pressure, fluid velocity, and height above some reference point. And so the faster the fluid is going, the less pressure it exerts on the walls of the container. If we increase the velocity, in order for this to still be equivalent on the other side, the pressure goes down. A fluid changing height applies more pressure at a lower elevation, greater depth. So as the height term gets bigger, again, the pressure goes down. As the height term gets smaller, the pressure term goes up in order for these to remain equivalent. Now you could of course change velocity and pressure at the same time, velocity and height at the same time, and I'll show you an example of that. But usually when you use Bernoulli's principle, you're going to be only fiddling with one thing and not the other. And so you can actually ignore one of these terms. If I give you a problem and the only thing that I am telling you is that the height changes, then you can just forget about the velocity term and just look at height and pressure. Or if I give you a pressure problem and tell you that velocity is changing but not height, you can forget that term, okay? So usually you don't have to mess with all three at one time. Let's look at an example. Here we have an example where fluid is in a certain diameter, a certain cross-sectional area, which then we will be able to use to figure out its velocity, right? So I have the velocity information here, and I have the pressure at this point in the pipe. And then the fluid both rises and gets bigger. When it rises, pressure is going to drop. And when it gets bigger, pressure is going to drop because the speed slows down. So all of those things you would be able to throw into an equation and manipulate using Bernoulli's principle. Okay? That's the kind of stuff we're going to be doing. Here's another picture of that. This is another way of expressing Bernoulli's equation. You may want to write that down. That could be helpful to you, but the textbook version is just as good. Okay? So again, here is the pressure at one point with a certain diameter, a certain area of the pipe has a certain pressure. It's a high pressure. It's a big opening, and it's low down. And then as the pipe rises, the pressure drops, and the pipe is going to get smaller, which means the velocity increases. As the velocity increases, the pressure is going to drop as well. So because of a slow fluid and low down, this is a higher pressure. Fast fluid and high up, this is a lower pressure. Okay, Bernoulli's principle. This plays into lift. So fluid dynamics has a lot to do with airplanes and spacecraft designs and things of that nature. Because of Bernoulli's effect, fluids forced to go faster create areas of low pressure, and those areas of low pressure can be used to draw materials into that area of low pressure. Okay, so we have wings on airplanes, and the general idea of a wing is that it creates a vacuum above the wing that sucks the airplane up into the air, and that's why it can fly. And that has to do with Bernoulli's principle. Okay, any device which generates lift in air is called an airfoil, and in a liquid we would call it a hydrofoil. It's the same thing. So I'm going to demonstrate Bernoulli's effect to you here, right? And this is a classic demonstration. I have this piece of paper hanging here, and right now the air above the paper and the air below the paper is not moving very much, and is moving at equally slow and boring speeds. But if I speed up the air above the paper goes up. And the reason it went up is because as I sped up the air above the paper, I created an area of low pressure. And that area of low pressure drew the paper up into that area. So one more time. There you go, Bernoulli's principle. Okay. There's another thing that comes into play with lift, and that is the yata effect. Coanda. There you go, Coanda effect. I don't speak whatever language that is, but the Coanda effect has talks about the fact that fluids flowing over a curved surface tend to follow that curvature, and so the air flowing over the top of a curved wing is going to keep following that curvature and compress the air underneath the wing. It's going to squish the air underneath the wing. And then the third law of pair force of pushing air down is going to push the thing pushing the air down up, right? Third law of pair. So the air goes down, the wing goes up. That's another reason why there is lift. So let me show you a diagram that puts all that together. That's not that one. There you go. There you go. Oh, not that kind of lift. Okay, just kidding. Here we go. Here we have fast air causes low pressure, and so there's lift because of Bernoulli's principle. The Cognata effect also has something to do with it. So the air here is being forced down because of the angle of attack. The air hits the wing and gets forced down, and then the air coming over the top of the wing follows this curvature and forces down. And so down on the air, up on the wing. And that's two reasons why airplanes fly. Here's another picture of that. Air hits the wing and goes down. Air follows the wing and goes down. And so air goes down, wing goes up. Also, you can see the area of low pressure here created by the faster moving air. Faster moving air, low pressure, wing gets sucked into the low pressure. So that's the two reasons why wings work. And now you can build an airplane, right? Okay. Real fluids versus imaginary ideal fluids. Real fluids do have intermolecular attractions, they do have friction, and they do have non-streamlined flow. So I just want to show you some things that have to do with real fluids, since we've been talking about pretend ones this whole time. Viscosity is a word that we use to measure the intermolecular attractions between particles of a fluid and their container. In other words, how sticky is the fluid? Does it stick to itself, and does it stick to its container? The greater the viscosity, the greater the stickiness, the more it resists flow. So viscosity is measured as a resistance to flow. Okay, and we use a term called the coefficient of viscosity to talk about how much a fluid is resisting flow, just like the coefficient of friction. Only for the coefficient of friction we use mu, the lowercase m sound in Greek. Here we use eta, the lowercase short e sound, and it looks like the letter N with a too long tail, okay? But that is in fact the e sound in Greek. Eta, that's a lowercase eta, and we use that to represent the viscosity, how viscous a fluid is, okay? Flowing particles closer to the wall of a tube are slower because of viscosity. They stick to the wall of the tube and are slow, whereas particles that don't get to see the tube go flying down the middle of the pipe. So viscosity is one aspect of a real fluid as opposed to an ideal one. So here's just some pictures for you. In ideal fluid, we say it's all flowing at the same rate, no matter where you measure it. That's not true. In truth, particles near the pipe are slower than particles in the middle of the pipe, because here their viscosity does attract the pipe and they do get slowed down by the pipe. Fluids in the middle that don't see the pipe go zipping past. Okay, here's just something to help you think about viscosity. Some fluids pour very easily, and then the more viscous it gets, the slower it pours. It's resistance to flow. Viscosity is resistance to flow. And that is all she wrote, folks. Please let me know if you have any questions. You can put them in the comments field below, or I'll see you tomorrow in class. God bless you. Have a wonderful day.